Swayam Prabha. Digital India. Educated India.
We will now consider calculation of stresses in thin cells, and these cells are such that there is some axis of symmetry and the wall thickness is small. They can be cylindrical, spherical, conical, toroidal, and in each case they are nothing but solids of revolution. Toroidal cell, it is like this, it looks like a ring, it is like a ring, and then the cross section here is circular. So, also cross section here is circular. So, that is the toroidal cell, and we get the generation of this cell by considering rotation of a circle about the axis of symmetry. Calculation of stresses in these cells are simpler, so we would like to consider them. You have already seen the stresses in thin cells which are cylindrical in shape. There are two stresses, one in the axial direction if it is a closed cylinder, and the magnitude of the stress is nothing but PR by 2T in the axial direction, and the stress in the circumferential direction is PR by T. You can imagine if the cell is spherical, what difference will come about. So, in the case of a spherical cell, think of it that this is the cell, and now the cell is of thickness T, let us say, everywhere, and the radius is R. You will find that at any point here you are going to get some principal stress in the, if you consider that this is your axial direction, there will be some stress in the axial direction, and then there is going to be also another stress which is going to act in the orthogonal direction, if you would like to call it circumferential stress, that is sigma 1. So, if this is that is sigma 2, if this is sigma 1 x, this is let us say axial stress, then that is the circumferential stress. To calculate the stress sigma 1, it is quite simple, that you take a section, vertical section, and if you take the vertical section here, to a larger scale I draw. So, this is the vertical section, you have some wall thickness, so the stresses are going to act in this direction. Since the cell is of small thickness, we can take the stress to be uniform everywhere, and that is what is of intensity sigma 1, and if R is the internal radius and T is the thickness, then obviously the total load which is counterbalancing the pressure here is nothing but 2 pi r into T into sigma 1. So, 2 pi r into T, that is the metallic area, multiplied by sigma 1, and it is counterbalancing the load acting in the opposite direction, which is acting on this circular area pi r square, and pressure is P. So, that gives us sigma 1 equal to P r by 2 T. Similarly, if you are interested in calculating the stress sigma 2, you take a horizontal section and it will come out to be the same. So, in the spherical cell you have the both hoop stress and the axial stress of the same magnitude, and that is the least stress that can happen. Let us consider now conical cell. So, if the cell is like this, that we have some angle alpha, you find that many a times the cylindrical cell has a end closure which is conical. So, therefore, it is necessary to calculate the stress at the wall of a conical cell. Let us say that internal pressure of this conical vessel is P, and we are interested in calculating the stresses at every point. We now consider, we just concentrate that there is a section here. This is section of radius, let us say r, and the wall thickness we will consider this wall thickness to be equal to T. If you consider the vessel to be like this, just concentrate on the vessel, say this is your normal to the wall. So, if this is the normal to the wall, so this angle is also alpha. Then you can see this portion, if you just concentrate on this portion, then this portion will appear to be a cylindrical vessel of radius this, that is nothing but r by cos alpha. So, the pressure which is acting on the wall is the internal pressure. So, you have as if a cylindrical vessel of radius is equal to r by cos alpha. So, if that is the case, then we can calculate the axial stress which is going to act in this direction. We will represent the axial stress by sigma 1, and the hoop stress which is going to act in the circumferential stress, that is by sigma 2 hoop stress. So, let us write that sigma 1 is axial stress and sigma 2 is hoop stress or circumferential stress. So, for a vessel with radius r by cos alpha, internal pressure P, the axial stress is going to be P r by 2 T. So, therefore, if we write that, that will be nothing but sigma 1 is equal to P r by cos alpha by 2 T. So, that is the value of sigma 1 stress, and therefore, sigma 1 will come out to be P r by 2 T cosine alpha, that is the axial stress. Now, the other stress which is the hoop stress, that will be nothing but P r by T. So, herein we have P r by cosine alpha by T. So, that will become P r by T cos alpha. So, therefore, sigma 2 is going to be P r by T cos alpha. So, these are the stresses at a point in a conical cell. So, it is going to remain constant, and you see that if alpha is equal to 0 degree, that becomes cylindrical cell, then you get back the formula for the cylindrical cell. To calculate this stress sigma 1, we can also follow another procedure. I need not use the formula that we have derived for the cylindrical cell. We can consider now, let us say we will take a section of the vessel at this point. So, if we take a section of the vessel here, it is like this. We have this radius is equal to r, and this is the stress sigma 1 acting on the material. This is sigma 1, and the pressure which is acting downward of the fluid. So, therefore, you see that we have the force acting due to the pressure is nothing but P into pi r square at that section, and now this is counterbalanced by the metallic forces which is acting over an area 2 pi r into T, that is the total area, and the intensity of the stress is sigma 1, and now we must take its component here in this direction, which is cosine alpha. So, therefore, we can have now sigma 1 into 2 pi r into T into cosine alpha. So, you have 2 pi r into T, cosine of sigma 1 is sigma 1 cosine alpha, that gives us the equilibrium equation, and this must finally, or this finally gives you sigma 1 equal to 2 T P r by 2 T cos alpha. So, that is what we have also obtained earlier by considering it to be a cylindrical vessel. Now, next thing we consider a toroidal cell. This sometimes made use of in plants. If we take this section, diametral section, it looks like this. You have two rings, and this is the other portion. So, it says semicircular thing which we have taken section here. Look at the dimensions, that the ring radius is capital R, and the wall or this cross sectional radius is equal to R, wall thickness is T, and the internal pressure acting on this vessel is as usual P. As I said that this cell is generated by revolving this circle about the axis of symmetry. So, the circumferential stress is going to be acting perpendicular to the plane of the paper, and for sure that if you consider the equilibrium in the circumferential direction, you will have pi r square into P is the load due to the fluid pressure, which is counterbalanced by the stresses acting over this metallic area, which is 2 pi r into T into sigma 2 is the stress. So, therefore, P r square is equal to 2 pi r T into sigma 2, and that gives you the stress in the circumferential direction very easily to be sigma 2 is equal to P r by 2 T. That is same as in the case of cylindrical vessel. Now, we would like to calculate the stress in the axial direction. Herein, you see the axial direction, if you consider this point, then this point will be subjected to some stresses like this in this direction at this point, that is nothing but sigma 1 here. So, sigma 2 is acting out of the paper, and this is going to act tangentially to this cross section here, that is what is sigma 1. We will calculate this stress, and let us concentrate on this point which is making an angle of theta with the vertical, and if I extend it, this will intersect here. if I now concentrate on this portion of the material, look at this portion of the material, we expect the stress in the axial direction. If we consider the theta to be small, we will have stress here is nothing but sigma 1, and this is also sigma 1, that is the stress they are acting. And now we have the pressure acting, fluid pressure acting, which is uniform intensity P. So, our focus is on this segment only, which is making an angle of theta with the vertical. If you consider now this portion and its whole circular portion of it, so therefore, we are trying to just consider this, revolve this thing about the axis of symmetry. So, if you just consider the revolution of this material portion about this axis, so you get one ring sort of, and therefore, the total load which is acting vertically upward we can calculate, and that load is balanced by the component of this stress acting in the vertical direction. So, this angle is also theta. So, that is also angle, I am sorry, that is 90 minus theta. So, if this is theta, this is theta, and therefore, this is 90 minus theta. This angle is with the vertical is 90 minus theta. So, therefore, the total force which is acting vertically upward, it is going to be that annular area of radius, which is nothing but this is what is capital R, and this one is nothing but R plus R sin theta. So, this R sin theta is this distance. So, therefore, R plus R sin theta. So, therefore, the total force acting on this annular area, which is nothing but pi p into R plus R sin theta whole square minus R square. So, that is the annular area, and that annular area, its vertical component will give us the total vertically upward force, and that is now counterbalanced by 2 pi R plus R sin theta into T, that is the metallic area, and sigma 1 is the intensity of the stress. So, that is the this stress, and its component of it is cosine 90 minus theta. So, cosine 90 minus theta, that gives you the stress at this point, and this sigma 1 obviously does not contribute to the vertical direction. So, therefore, once you simplify this, you get the stress sigma 1 axial stress, and this is nothing but P R sin theta. So, it is a square minus b square form. So, we can write that this is 2 R sin theta divided by 2 T sin theta into R plus R sin theta. So, that is the stress, and once you simplify this, it becomes P R by 2 T 2 R plus R sin theta by R plus R sin theta, that is the value, and we can now make it slightly differently. We can write it as P R by 2 T 2 minus R sin theta R plus R sin theta. So, that is the axial stress in a torus. So, the hoop stress is remaining constant like a cylindrical shell, but then the axial stress, its value is going to change from point to point on the circumference of a cross section. So, it is very important to note the variation of the stress, and then you can understand what sort of failure can take place in a torus and how they can be prevented. So, let us plot the variation of the stress sigma 1, let us write once again PR by 2t 2 minus r sin theta by r plus r sin theta. So, we draw the circumference of the cross section. Let us write this point to be A, the vertical point, vertically topmost point is B, and this furthest point from the center. So, center of curvature is somewhere this side, and this bottommost point is, let us say, D, and our reference direction is this one. So, this is what is theta direction. Now, look at this. If theta equal to 0, then we have PR by 2t as the stress. So, therefore, if we now plot in the radial direction the magnitude of the stress, so therefore, I am going to get the magnitude of the stress here is PR by t. Theta is 0, this will become 2 will cancel, so PR by t. Similarly, if theta is equal to 180 degree, so if you consider the exactly opposite point there, D point, it is going to give us exactly the same magnitude of the stress. For theta equal to pi, this is again 0. Look at this. If I now consider theta equal to 90 degree, so it is 1. So, therefore, PR by 2t 2 minus r by r plus r. So, the magnitude of the stress here at this point is going to be PR by 2t 2 minus r by r plus r. So, here we find that the magnitude of the stress has reduced, and that is the minimum value of the stress that we can get on this section. So, this is the minimum stress at the outermost point. Similarly, if you find that the picture is going to gradually vary from this stress to this minimum. So, therefore, the variation is gradually it is like this. So, minimum, and then it is going to pick up value. Now, let us consider theta equal to minus. If theta equal to minus 90 degree, that means you come to this point. Herein actually sin theta is minus 1. So, therefore, it becomes 2 plus r by r minus r. So, here you find that some addition is there over 2, which is nothing but r by r minus r. So, therefore, that is actually going to give us the highest stress. So, at this point you get the highest stress, and you find that it is a symmetric picture on this portion with the portion here. So, therefore, the variation of stress you find here that it is gradually increasing, and you have the highest stress at this point. Similarly, you find the picture, same picture is repeated here. So, this is this, and here this stress variation is like. So, therefore, you see that the stress is gradually becoming, it is increasing and taking up the highest value there, and this distance, in fact, this radial distance we are plotting the magnitude of the stress for any theta value. So, this is radial plot we call. So, this is the radial plot of the stresses, and everywhere it is tensile stress. This point is known as crotch. Point A is known as crotch point, and you find that the value of the stress at this point is PR by 2T 2 plus R by R minus R. So, therefore, here it is highest, here it is smallest, and here they are same, and it is nothing but PR by T. So, this is your variation of sigma 1 on the circumference of the cross section. Now, why do you expect the failure to occur? For a torus like this, where do you expect the failure to occur? The stress is highest here, and it is lowest at this point, and it is going to be like that of a cylindrical vessel at this point B and D. So, therefore, C and A, in fact, C is the lowest stress. So, therefore, it is a safe point, and here it is highest stress. Unfortunately, although it is highest, it is not a critical point, it is, they are considered to be safer locations, whereas this B and D are considered to be critical. This is something very funny. You see that here you have the highest stress, and we consider that to be not very critical. It is mostly, you will find that torus is going to fail at this 12 o'clock position and 6 o'clock position. If it is failing, it will fail at the 12 o'clock and 6 o'clock position, it will not fail at the 3 o'clock and 9 o'clock position. Why that is so? This is something we should be able to understand. After all, we try to take a straight pipe, let us say we take a straight pipe like this, and this straight pipe is bent into the form of a torus. So, when you do that, you are trying to bend it like this, so when you are bending it like this, you are trying to generate compressive stress in the axial direction. So, when you are generating compressive stress in the axial direction, you are going to get thickening of the wall at this location. On the other hand, you find here the tensile stresses are generated at the outer fiber, and it is going to lead to thinning of the wall there. So, therefore, you see that during the process of manufacture itself, you are going to find wall thickness to be higher, and here it is reducing, and that thickening of the wall will take care of the extra stresses here, and here it is getting thinning down, and therefore, here the stress is reducing. So, naturally they are taken care of, whereas these points are not really going to be affected to that extent, and therefore, for such cells or configurations, you will find that these are not the critical locations, it is going to be B and D are the critical locations. So, the thinning of the wall can take care of the extra stress that is coming up here, and it is not, thickness is increasing. So, your stress is increasing, but at the same time thickness is increasing. So, therefore, it will take care of. On the other hand, here it is stress is reducing, wall is also thinning, so it is not a problem at all. On the other hand, at this location B and D, it does not change much, and here it will become critical, particularly at the top of the cell. You will find that these locations are neutral axis location. So, this location B and D comes on the neutral axis. See, it does not change. So, at the neutral axis there is no thinning or thickening, and therefore, these B and D points remains critical point for the torus. Now, we will consider that for general cells which have double curvature, how do you find out the stresses in such cells, and they are also cells of revolution. So, let us consider a general cell and then try to derive the stresses, how are they going to be related. So, let us look into that problem. So, let us consider general membrane, this is known as general membrane theory. We will try to consider a cell of revolution which is doubly curved. So, this is the shell of revolution, and this is the axis. This is the axis. Let us concentrate on an element here. This element, let us say that this is making an angle here at the center, and this radius of curvature is equal to R2. So, therefore, the stress which is going to act on this face is nothing but hoof stress sigma 2, and similarly the stress which is going to act on this face, that is equal to sigma 2. Now, the curvature of this edge, let us consider this curvature. This curvature of this edge is equal to R1. So, the wall thickness, let us consider this small element, we consider that thickness is uniform. So, that is the element we will be concentrating upon. So, therefore, there will be pressure acting all over the inner surface, and that will act outward. So, the pressure loading is going to act in this direction. So, if we now try to look at the picture again. So, this edge is like this, it is making an angle of d theta 1, the pressure is P and radius is R1, and this is the say sigma 1, that is the axial stress. So, therefore, you know that this is the stress which is acting on this edge is sigma 1. Similarly, if we consider this sector, this is making an angle of, let us say, d theta 2, this is d theta 2, the radius is R2, and the pressure is acting in the radial direction P. Stresses at the edges is nothing but sigma 2. So, in the R2 sector we are having stresses sigma 2, and here it is R1 sector, we have the stresses equal to sigma 1. Let us now try to consider the equilibrium in the radial direction. So, if we try to sum up the forces in the radial direction, so if I now try to take this area, this length is nothing but R2 d theta 2, and this area is R1 d theta 1. So, therefore, the total area we can take approximately to be R1 R2 d theta 1 d theta 2, and the pressure P is acting radially outward. So, therefore, we have P into R1 d theta 1 R2 d theta 2 as if it is a rectangular area. So, that is the radially outward load, and it is counterbalanced by the component of these in the center towards the center. So, therefore, this angle is d theta 1 by 2. So, therefore, we can now consider what is this area. This area is nothing but R2 into d theta 2 into T into sigma theta 1, and its sine component, sine d theta by 2 component. So, we can write now sigma 1 r2 d theta 2 into t. So, that is this force and its sine component sine d theta 1 by 2. So, this angle is nothing but d theta 1 by 2, and we have one contribution from this side, another contribution from this side. So, therefore, we can multiply by 2. So, we get the contribution from these two edges. Similarly, if I try to consider these forces which are here, again it is going to make an angle here which is of d theta 2 by 2. So, I can write now sigma 2 acting over an area of r1 d theta 1 into t and the sine d theta by 2 component. So, sine d theta 2 by 2 component, and we have one from this side, another from that side. So, multiply by 2. So, that is therefore, finally, you find that we can substitute this thing as d theta 1 by 2 for small angle, and this can be substituted by d theta by 2, and these 2 and that 2 will cancel, this 2 and that 2 will cancel. Finally, you will find r1 r2 d theta 1 d theta 2 will be common, and you find that final relationship is p by 2 p by t is equal to sigma 1 by r1 plus sigma 2 by r2. So, this is the general membrane formula. The two principal stresses acting at a point in a doubly curved shell of revolution is related to pressure and thickness by this relationship, and this relationship is also very useful in determining the one of the stresses if you know the other stress. More often you will find that the axial stress can be found out easily, then the other component of the stress, hoop stress, can be found out by making use of this formula. So, this is the general membrane theory for doubly curved shell. We will quickly consider applications of the formula to some of the known results. Think of it, you have a cylindrical shell here, and this cylindrical shell is of radius r and wall thickness t. We have the stress sigma 1 acting in the axial direction, and circumferential stress is sigma 2, and therefore, this r1 in this case, which is infinity, and r2 is going to be r. So, if I now apply the formula sigma 1 by r1 sigma 2 by r2 is equal to p by t, and since r1 is infinity, this terms goes off. So, you have now sigma 2 by r is equal to p by t, and therefore, sigma 2 is equal to p r by t. So, it follows from the formula that we have derived. Let us consider the second example. Think of the conical vessel with the vertex angle equal to alpha at any point at a distance r. If I now look into sigma 1 stress is going to act in the wall thickness wall direction, and therefore, this is sigma 1, and the radius of curvature for this direction is infinity, and the other stress which is going to be hoop stress, for that the radius is nothing but r1 by cos alpha. So, this radius is r1 by cos alpha, that is r2. So, if I now try to substitute in this formula sigma 1 by r1 plus sigma 2 by r2, which is r by cos alpha, equal to p by t, again this term knocks out, and we have sigma 2 equal to pr by t cosine alpha. So, that results we have already derived in a different way. Let us consider the case of the torus. This is something very typical. So, in the case of a torus, we have the hoop stress which is going to act perpendicular to the plane of the paper. That stress is going to be given by sigma 2, which is pr by 2t, very easy to determine. Now, we are interested in finding out the axial stress sigma 1 acting like this, and this axial stress, obviously the radius of curvature for that is this r. So, r1 is equal to r. And what about the radius of curvature of the vessel in the the sigma 2 direction. So, that is nothing but this radius of curvature, this is the center of curvature for this point, and therefore, if we now consider that radius for the axial direction, that is going to be nothing but this distance is r, this angle is equal to theta, and therefore, this is nothing but r by sin theta, capital R by sin theta plus this small r. So, therefore, this radius for the direction r2 is nothing but r by sin theta plus r. So, again if we try to substitute in the formula, sigma 1 by r1 is r, sigma 2 by r2 which is this expression, and that is equal to p by 2, and then you find that sigma 1 by r is equal to p by 2t. If I take it to the other side, it becomes 2 minus r sin theta by r plus sin theta, and therefore, sigma 1 equal to pr by 2t into 2 minus r sin theta by r plus r sin theta. So, this formula can also be derived considering the general membrane theory. Now, we will like to consider some problem solving using the derivations that we have got. First example, let us consider on thin cylindrical cell. It is given that there is a pipe of internal radius 50 millimeter, thickness of the wall 3 millimeter, the material has a yield stress 375 megapascal, factor of safety equal to 4, find out the safe pressure that this pipe can be subjected to. So, here obviously we can use the maximum normal stress theory or maximum shear stress theory. In either case, we will have the maximum principal stress is equal to the yield point divided by the factor of safety. So, the design equation becomes, in this case obviously we have the highest stress is hoop stress, which is nothing but sigma 2 equal to PR by T. So, sigma 2 is equal to PR by T, and that should be limited by sigma y by the factor of safety, and therefore, once you do the calculations, you get this P so that gives you now 5.625 MPa. Let us consider another example. On a thin spherical cell. The spherical cell is with the following details. Again, it is a thin cell which is filled with water at atmospheric pressure. Its internal diameter is 300 millimeter, wall thickness is 1.6 millimeter, material property Poisson's ratio is 0.3, and it is having modulus 100 GPa. It is really made up of copper, and the bulk modulus of water is 200 GPa. Now, what is specified here, that this vessel is full with water at atmospheric pressure, and now 25 cc of water is injected into the vessel. So, 25 cc of water is injected into the vessel, and what is needed to be found out? Find out the pressure that develops because of this insertion of the fluid. So, extra fluid is inserted into the vessel, and due to that there will be some pressure rise in the vessel. Find out that pressure. How do you go about it? If I now look at the problem, it is like this. We have this water already there, and now if I think of it that I am trying to add 25 cc to it, and let us say that at atmospheric pressure, think of it that it is a spherical cell of water without any cover, and now you try to add on to it 25 cc, and therefore its diameter is going to be now more, and let us say that if there is no vessel, then it will try to take up outer boundary position like this. So, that is the, therefore, this to this it correspond to, so this span corresponds to that extra water delta V W. Obviously, the vessel is already in position. This water insertion cannot be taking place at atmospheric pressure. As you try to put in little bit of water, it will try to expand the copper vessel, and that copper vessel will try to compress the water inside. So, this sort of tug of war will continue, and what you will find finally that when you have tried to add that full 25 cc, you will find that the vessel wall is not going to really get expanded up to that position. It is going to be somewhere in between, and it will try to compress the outer surface of the water to the same position. So, what happens that this 25 cc of water that we have added, it is going to expand the vessel by this much, and the pressure that develops in the vessel, that pressure will compress the water cell from this point to that point. So, therefore, if we now mark it that the equilibrium vessel position is, let us say, this one, so this is the final wall position. What we find really that the water, this is the sphere of water, it got compressed. Let us say that it got compressed by some volume which is delta V2, and the copper vessel got expanded by this much, which is equal to delta V1. So, it is obvious that this total volume of water that we have inserted, it is going to be nothing but delta V1 plus delta V2. Now, we can calculate what is delta V1, because the internal pressure of water will try to expand the copper vessel by delta V1, and the pressure which is acting on the outer surface of the water sphere, that will try to compress it by delta V2, and therefore, we can calculate both the things under the same pressure, and then we can write the compatibility condition that delta V1 plus delta V2 equal to delta VW. So, I have written here that delta V1 plus delta V2 is equal to delta VW. So, that is the equation number 1, which is nothing but compatibility condition. Now, how do you calculate let us say delta V2? Delta V2, the expansion of the, let us see that this is, I will write this delta V1, expansion of the copper vessel. So, the copper vessel under the action of the pressure P, it is going to have some radial expansion. Let us say that that radial expansion is equal to delta R. So, that delta R by R is nothing but hoop strain. So, if that is the hoop strain, the volumetric expansion is going to be 3 times of that strain. So, therefore, if the strain in the circumferential direction is delta V by R, then the volumetric strain is going to be delta 3 times delta R by R. So, therefore, the volume increase, if initial volume of the sphere internal volume is V, then that is the increase in the volume. So, that is nothing but we can write this thing as radial displacement of the wall divided by r. This delta r is nothing but again u, displacement of the wall, and for a spherical vessel you can calculate the hoop strain, which is nothing but it is u by r is given by hoop stress sigma 2 by E minus nu times axial stress by E, nu times axial. And for the spherical vessel it is therefore both sigma 1 and sigma 2 is nothing but PR by 2T. So, therefore, PR by 2TE multiplied by 1 minus nu. So, therefore, you got this U. And now, what is delta V2? Delta V2 is the compression of the water sphere, and that should be available from P by V plus delta VW, that is the total volume of the water divided by the bulk modulus. You see, you know that this delta V by V, we have the formula delta V by V is equal to P by K, that is the bulk modulus, and therefore, we can write the same thing here, that this delta V2 is equal to P into the volume divided by K, and this V plus delta VW we can write that thing approximately equal to V, and therefore, this is V by K into P. So, everything is available in terms of pressure, and now from the compatibility equation, therefore, we can now write delta V1 plus delta V2 is equal to delta VW, and you substitute the values. The volume of the sphere is nothing but 4/3 pi r cube. So, I am writing that to be common, and that multiplied by we have the pressure of course P by K bulk modulus of water, plus if we write this one, it is nothing but PR by 2T E of copper multiplied by 1 minus nu, that is equal to VW, which is nothing but 25 cc, which is in millimeter unit, it is 10 to the power 3 millimeter cube. So, here you have written everything in terms of millimeter unit, Newton millimeter unit, and R is nothing but 150 millimeter, and all the values KW 2 GPa, EC is 100 GPa, nu is 0.3, R is given 150. So, therefore, all that once you substitute, we find 4 by 3 50 cube P by 2 into 10 to the power 3 plus P 150 into 1 minus nu is 0.7, 2 into 1.6 into 100 into 10 to the power 3 is equal to 25 into 10 to the power 3. So, that is what you have the expression to calculate P, and P once you calculate it comes out to be 2.13 megapascal. So, that is the pressure which is going to develop. So, this is the way this sort of problem can be tackled. Now, I would like you to think about another problem which is also very interesting, and it is solvable along similar lines. Think of a vessel that you have a vessel here, it is filled with water and its dimensions are ID 600 millimeter, thickness is 6 millimeter, and the water is initially at 25 degrees centigrade. Now, the water of the temperature of the water is raised by 10 degree. So, it is made to 35 degrees centigrade. Now, you have to calculate what is the stress in the vessel given the information that the volumetric expansion at atmosphere in this temperature range is going to be 0.0059 units per unit volume. Bulk modulus of water is 2 GPa. Nu S, this is a steel material, and it is nu S is equal to 0.3, Es is equal to 200 GPa, and the thermal coefficient of expansion of steel is 12 into 10 to the power minus 6 per degree centigrade. So, therefore, in this case what is given here is that you are trying to raise the temperature of water by 10 degree centigrade. Because of that rise, the volume of water is going to rise at this rate. So, you can find out the volumetric increase of the water volume, and once you have done that, now you will find that if the vessel is allowed to, or the water is allowed to expand freely, it will take up some position up to, let us say, this position. At the because of the temperature rise, vessel is going to expand up to this position, it will expand radially. So, there is a net change in the volume, and this volume now becomes delta V W as in the previous case. So, in this case your volume increase in the water is not exactly delta V W, it is going to be that change in the volume of water minus the increase in the size of the cell due to the temperature rise, that will become delta V W, and then this is going to be balanced by increase in the vessel dimension, let us say that is delta V1, and decrease in the water volume is equal to delta V2. So, increase in the water volume. So, finally, let us say they are in equilibrium somewhere there. So, for that equilibrium position, what you will find that increase in the volume of cell is delta V1, decrease in the volume of water is delta V2, that is going to be in compatibility with delta VW. So, you can solve this problem, and in this case the answer is going to be 363.3 MPa.